so before we can start talking about trig derivatives, we're going to talk about trig limits, okay? So for this video, we're going to talk about how to evaluate them graphically, okay? So this will be a more visual, obviously graphical, and we are going to recall what dampening means and the squeeze theorem. So hopefully those are ringing a bell in your head right now. Okay, so limits of trig functions. Here's our first example. So we have the limit as x approaches 0 of sine of 1 over x. Now, let's take a look at what's happening as we approach 0 from the left and as we approach 0 from the right. And you notice in the middle here, we would consider this to be oscillating. Okay, so it's continuing to go back and forth and back and forth and back and forth. You could also think about this in terms of like actual values. So what is the value if x was 2 over pi, or 2 over 3 pi, or 2 over 5 pi, and so on? Well, those values that I just listed off are getting closer to 0, but their y values are oscillating between 1 and -1. So because of that reason, because it's oscillating here, this limit does not exist. Okay? From the left and from the right, as we approach 0, it oscillates between -1 and 1. There's no finite limit. Let's take a look at this example. How about the limit as x approaches 0 of x times 1 or sine of 1 over x? So before, we just looked at sine of 1 over x, and we said that that doesn't exist. But what happens when we multiply by x? And if you're thinking, ooh, dampening factor, you're right, it is. Now, if I take a look at the difference of its graph, okay, so now you notice it does look like it's kind of oscillating a little bit, but as we get closer and closer to 0, what do our y values get closer and closer to? Very good. We would say that this limit is, that this is, technical difficulties over here. That this is 0, okay? So the y values appear to be approaching 0. As I kind of alluded to in the intro of this video, we would use our squeeze theorem here, okay? So notice, just as a quick reminder, squeeze theorem, this was from Unit 7, right? If we know that we have 3 functions, h of x, and f of x, and g of x, and f of x is between h and g, we know that there are limits as we approach some value c. Well, the limit of f would equal whatever these guys are, because they would squeeze them together, right? So in the middle here, they'd all be equal. So it's the same idea here, okay? Because x is our dampening factor here. Oops. I apologize for this craziness. Well, according to our squeeze theorem, well, we know that the negative absolute value of x is less than or equal to x sine of 1 over x, which is less than or equal to the absolute value of x. And if you're wondering why it's absolute value, well, remember that we're approaching 0. So you have to think about approaching 0 from the left and approaching 0 from the right when it comes to x. So that's why we have our absolute value here. And because we know the limits of as x approaches 0 of negative absolute value of x, and the limit as x approaches 0 of absolute value of x are both 0, then the limit as x approaches 0 of this function that's between the two must also be 0. Okay, so x sine of 1 over x is squeezed in between negative absolute value of x and positive. Okay, so that's how that squeeze theorem is applied here. Okay. Here's another example as well. So notice this is a new function. We have limit as x approaches 0 of x times sine of 10x. Well, similar situation, as x is getting closer to 0 from both sides, notice that our function is also getting closer and closer to 0. Squeeze theorem. Alright, so one thing that we're going to be using coming ahead is our trig identities. So make sure that you recall them. As it says here, you will not be given them on your tests. We want to understand the squeeze theorem and how it works, and also what a dampening factor is and how it affects a graph.